In thermodynamics, heat is energy in transfer between a thermodynamic system and its surroundings by modes other than thermodynamic work and transfer of matter. Such modes are microscopic, mainly thermal conduction, radiation, and friction, as distinct from the macroscopic modes, thermodynamic work and transfer of matter. For a closed system, transfer of matter excluded, the heat involved in a process is the difference in internal energy between the final and initial states of a system, and subtracting the work done in the process. For a closed system, this is the formulation of the first law of thermodynamics. Calorimetry is measurement of quantity of energy transferred as heat by its effect on the states of interacting bodies, for example, by the amount of ice melted or by change in temperature of a body. In the International System of Units, SI, the unit of measurement for heat, as a form of energy, is the joule, J. With various other meanings, the word heat is also used in engineering, and it occurs also in ordinary language, but such are not the topic of the present article. As a form of energy, heat has the unit joule, J, in the International System of Units, SI. In addition, many applied branches of engineering use other, traditional units, such as the British thermal unit, BTU, and the calorie. The standard unit for the rate of heating is the watt, W, defined as 1 joule per second. The symbol Q for heat was introduced by Rudolf Clausius and Macquorn Rankine in c. 1859. Heat released by a system into its surroundings is by convention, as a contributor to internal energy, a negative quantity. When a system absorbs heat from its surroundings, it is positive, Q0. Heat transfer rate, or heat flow per unit time, but it is not a time derivative of a function of state, which can also be written with the dot notation, since heat is not a function of state. Heat flux is defined as rate of heat transfer per unit cross-sectional area, watts per square meter. A calorimeter is a device used for measuring heat capacity, as well as the heat absorbed or released in chemical reactions or physical changes. Referring to conduction, Partington writes, if a hot body is brought in conducting contact with a cold body, the temperature of the hot body falls and that of the cold body rises, and it is said that a quantity of heat has passed from the hot body to the cold body. Referring to radiation, Maxwell writes, in radiation, the hotter body loses heat, and the colder body receives heat by means of a process occurring in some intervening medium which does not itself thereby become hot. Maxwell writes that convection as such is not a purely thermal phenomenon. In thermodynamics, convection in general is regarded as transport of internal energy. If, however, the convection is enclosed and circulatory, then it may be regarded as an intermediary that transfers energy as heat between source and destination bodies, because it transfers only energy and not matter from the source to the destination body. In accordance with the first law for closed systems, energy transferred solely as heat leaves one body and enters another, changing the internal energies of each. Transfer, between bodies, of energy as work is a complementary way of changing internal energies. Though it is not logically rigorous from the viewpoint of strict physical concepts, a common form of words that expresses this is to say that heat and work are interconvertible. Cyclically operating engines that use only heat and work transfers have two thermal reservoirs, a hot and a cold one. They may be classified by the range of operating temperatures of the working body, relative to those reservoirs. In a heat engine, the working body is at all times colder than the hot reservoir and hotter than the cold reservoir. In a sense, it uses heat transfer to produce work. In a heat pump, the working body, at stages of the cycle, goes both hotter than the hot reservoir, and colder than the cold reservoir. In a sense, it uses work to produce heat transfer. In classical thermodynamics, a commonly considered model is the heat engine. It consists of four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A cyclic process leaves the working body in an unchanged state, and is envisaged as being repeated indefinitely often. Work transfers between the working body and the work reservoir are envisaged as reversible, and thus only one work reservoir is needed. But two thermal reservoirs are needed, because transfer of energy as heat is irreversible. A single cycle sees energy taken by the working body from the hot reservoir and sent to the two other reservoirs, the work reservoir and the cold reservoir. The hot reservoir always and only supplies energy, and the cold reservoir always and only receives energy. The second law of thermodynamics requires that no cycle can occur in which no energy is received by the cold reservoir. Heat engines achieve higher efficiency when the ratio of the initial and final temperature is greater. Another commonly considered model is the heat pump or refrigerator. Again, there are four bodies: the working body, the hot reservoir, the cold reservoir, and the work reservoir. A single cycle starts with the working body colder than the cold reservoir, and then energy is taken in as heat by the working body from the cold reservoir. Then the work reservoir does work on the working body, adding more to its internal energy, making it hotter than the hot reservoir. The hot working body passes heat to the hot reservoir, but still remains hotter than the cold reservoir. Then, by allowing it to expand without passing heat to another body, the working body is made colder than the cold reservoir. It can now accept heat transfer from the cold reservoir to start another cycle. The device has transported energy from a colder to a hotter reservoir, but this is not regarded as by an inanimate agency, rather, it is regarded as by the harnessing of work. This is because work is supplied from the work reservoir, not just by a simple thermodynamic process, but by a cycle of thermodynamic operations and processes, which may be regarded as directed by an animate or harnessing agency. Accordingly, the cycle is still in accord with the second law of thermodynamics. The efficiency of a heat pump, which exceeds unity, is best when the temperature difference between the hot and cold reservoirs is least. Functionally, such engines are used in two ways: distinguishing a target reservoir and a resource or surrounding reservoir. A heat pump transfers heat to the hot reservoir as the target from the resource or surrounding reservoir. A refrigerator transfers heat, from the cold reservoir as the target, to the resource or surrounding reservoir. The target reservoir may be regarded as leaking. When the target leaks heat to the surroundings, heat pumping is used. When the target leaks coldness to the surroundings, refrigeration is used. The engines harness work to overcome the leaks. In the kinetic theory, heat is explained in terms of the microscopic motions and interactions of constituent particles, such as electrons, atoms, and molecules. The immediate meaning of the kinetic energy of the constituent particles is not as heat. It is as a component of internal energy. In microscopic terms, heat is a transfer quantity, and is described by a transport theory, not as steadily localized kinetic energy of particles. Heat transfer arises from temperature gradients or differences, through the diffuse exchange of microscopic kinetic and potential particle energy, by particle collisions and other interactions. An early and vague expression of this was made by Francis Bacon. Precise and detailed versions of it were developed in the 19th century. In statistical mechanics, for a closed system, no transfer of matter, heat is the energy transfer associated with a disordered, microscopic action on the system, associated with jumps in occupation numbers of the energy levels of the system, without change in the values of the energy levels themselves. It is possible for macroscopic thermodynamic work to alter the occupation numbers without change in the values of the system energy levels themselves, but what distinguishes transfer as heat is that the transfer is entirely due to disordered, microscopic action, including radiative transfer. A mathematical definition can be formulated for small increments of quasi-static adiabatic work in terms of the statistical distribution of an ensemble of microstates. Quantity of heat transferred can be measured by calorimetry, or determined through calculations based on other quantities. Calorimetry is the empirical basis of the idea of quantity of heat transferred in a process. The transferred heat is measured by changes in a body of known properties, for example, temperature rise, change in volume or length, or phase change, such as melting of ice. A calculation of quantity of heat transferred can rely on a hypothetical quantity of energy transferred as adiabatic work and on the first law of thermodynamics. Such calculation is the primary approach of many theoretical studies of quantity of heat transferred. A red-hot iron rod from which heat transfer to the surrounding environment will be primarily through radiation. The discipline of heat transfer, typically considered an aspect of mechanical engineering and chemical engineering, deals with specific applied methods by which thermal energy in a system is generated, or converted, or transferred to another system. Although the definition of heat implicitly means the transfer of energy, the term heat transfer encompasses this traditional usage in many engineering disciplines and layman language. Heat transfer is generally described as including the mechanisms of heat conduction, heat convection, thermal radiation, but may include mass transfer and heat in processes of phase changes. Convection may be described as the combined effects of conduction and fluid flow. From the thermodynamic point of view, heat flows into a fluid by diffusion to increase its energy. The fluid then transfers, advex, this increased internal energy, not heat, from one location to another, and this is then followed by a second thermal interaction which transfers heat to a second body or system, again by diffusion. This entire process is often regarded as an additional mechanism of heat transfer, although technically, heat transfer and thus heating and cooling occurs only on either end of such a conductive flow, but not as a result of flow. Thus, conduction can be said to transfer heat only as a net result of the process, but may not do so at every time within the complicated convective process. In an 1847 lecture entitled On Matter, Living Force, and Heat, James Prescott Joule characterized the terms latent heat and sensible heat as components of heat each affecting distinct physical phenomena, namely the potential and kinetic energy of particles, respectively. He described latent energy as the energy possessed via a distancing of particles where attraction was over a greater distance, i.e. a form of potential energy, and the sensible heat as an energy involving the motion of particles, i.e. kinetic energy. Latent heat is the heat released or absorbed by a chemical substance or a thermodynamic system during a change of state that occurs without a change in temperature. Such a process may be a phase transition, such as the melting of ice or the boiling of water. Heat capacity is a measurable physical quantity equal to the ratio of the heat added to an object to the resulting temperature change. The molar heat capacity is the heat capacity per unit amount, SI unit, mole, of a pure substance, and the specific heat capacity, often called simply specific heat, is the heat capacity per unit mass of a material. Heat capacity is a physical property of a substance, which means that it depends on the state and properties of the substance under consideration. The specific heats of monatomic gases, such as helium, are nearly constant with temperature. Diatomic gases such as hydrogen display some temperature dependence, and triatomic gases, example carbon dioxide, still more. Before the development of the laws of thermodynamics, heat was measured by changes in the states of the participating bodies. Some general rules, with important exceptions, can be stated as follows. In general, most bodies expand on heating. In this circumstance, heating a body at a constant volume increases the pressure it exerts on its constraining walls, while heating at a constant pressure increases its volume. Beyond this, most substances have three ordinarily recognized states of matter: solid, liquid, and gas. Some can also exist in a plasma. Many have further, more finely differentiated, states of matter, such as glass and liquid crystal. In many cases, at fixed temperature and pressure, a substance can exist in several distinct states of matter in what might be viewed as the same body. For example, ice may float in a glass of water. Then the ice and the water are said to constitute two phases within the body. Definite rules are known, telling how distinct phases may coexist in a body. Mostly, at a fixed pressure, there is a definite temperature at which heating causes a solid to melt or evaporate, and a definite temperature at which heating causes a liquid to evaporate. In such cases, cooling has the reverse effects. All of these, the commonest cases, fit with the rule that heating can be measured by changes of state of a body. Such cases supply what are called thermometric bodies, that allow the definition of empirical temperatures. Before 1848, all temperatures were defined in this way. There was thus a tight link, apparently logically determined, between heat and temperature, though they were recognized as conceptually thoroughly distinct, especially by Joseph Black in the later 18th century. There are important exceptions. They break the obviously apparent link between heat and temperature. They make it clear that empirical definitions of temperature are contingent on the peculiar properties of particular thermometric substances, and are thus precluded from the title absolute. For example, water contracts on being heated near 277 K. It cannot be used as a thermometric substance near that temperature. Also, over a certain temperature range, ice contracts on heating. Moreover, many substances can exist in metastable states, such as with negative pressure, that survive only transiently and in very special conditions. Such facts, sometimes called anomalous, are some of the reasons for the thermodynamic definition of absolute temperature. In the early days of measurement of high temperatures, another factor was important, and used by Josiah Wedgwood in his pyrometer. The temperature reached in a process was estimated by the shrinkage of a sample of clay. The higher the temperature, the more the shrinkage. This was the only available more or less reliable method of measurement of temperatures above 1000 degrees Celsius 1832 degrees Fahrenheit. But such shrinkage is irreversible. The clay does not expand again on cooling. That is why it could be used for the measurement. But only once. It is not a thermometric material in the usual sense of the word. Nevertheless, the thermodynamic definition of absolute temperature does make essential use of the concept of heat, with proper circumspection. The property of hotness is a concern of thermodynamics that should be defined without reference to the concept of heat. Consideration of hotness leads to the concept of empirical temperature. All physical systems are capable of heating or cooling others. With reference to hotness, the comparative terms hotter and colder are defined by the rule that heat flows from the hotter body to the colder. If a physical system is inhomogeneous or very rapidly or irregularly changing, for example by turbulence, it may be impossible to characterize it by a temperature, but still there can be transfer of energy as heat between it and another system. If a system has a physical state that is regular enough, and persists long enough to allow it to reach thermal equilibrium with a specified thermometer, then it has a temperature according to that thermometer. An empirical thermometer registers degree of hotness for such a system. Such a temperature is called empirical. For example, Truesdell writes about classical thermodynamics: at each time, the body is assigned a real number called the temperature. This number is a measure of how hot the body is. Physical systems that are too turbulent to have temperatures may still differ in hotness. A physical system that passes heat to another physical system is said to be the hotter of the two. More is required for the system to have a thermodynamic temperature. Its behavior must be so regular that its empirical temperature is the same for all suitably calibrated and scaled thermometers, and then its hotness is said to lie on the one-dimensional hotness manifold. This is part of the reason why heat is defined following Karateadori and Born, solely as occurring other than by work or transfer of matter. Temperature is advisedly and deliberately not mentioned in this now widely accepted definition. This is also the reason that the zeroth law of thermodynamics is stated explicitly. If three physical systems, A, B, and C are each not in their own states of internal thermodynamic equilibrium, it is possible that, with suitable physical connections being made between them, A can heat B and B can heat C and C can heat A. In non-equilibrium situations, cycles of flow are possible. It is the special and uniquely distinguishing characteristic of internal thermodynamic equilibrium that this possibility is not open to thermodynamic systems, as distinguished amongst physical systems, which are in their own states of internal thermodynamic equilibrium. This is the reason why the zeroth law of thermodynamics needs explicit statement. That is to say, the relation is not colder than between general non-equilibrium physical systems is not transitive, whereas, in contrast, the relation has no lower a temperature than between thermodynamic systems in their own states of internal thermodynamic equilibrium is transitive. It follows from this that the relation is in thermal equilibrium with is transitive, which is one way of stating the Zeroth law. Just as temperature may be undefined for a sufficiently inhomogeneous system, so also may entropy be undefined for a system not in its own state of internal thermodynamic equilibrium. For example, the temperature of the solar system is not a defined quantity. Likewise, the entropy of the solar system is not defined in classical thermodynamics. It has not been possible to define non-equilibrium entropy, as a simple number for a whole system, in a clearly satisfactory way. Heat, energy that is transferred from one body to another as the result of a difference in temperature. If two bodies at different temperatures are brought together, energy is transferred, i.e., heat flows from the hotter body to the colder. The effect of this transfer of energy usually, but not always, is an increase in the temperature of the colder body and a decrease in the temperature of the hotter body. A substance may absorb heat without an increase in temperature by changing from one physical state, or phase, to another, as from a solid to a liquid, melting, from a solid to a vapor, sublimation, from a liquid to a vapor, boiling, or from one solid form to another, usually called a crystalline transition. The important distinction between heat and temperature, heat being a form of energy and temperature a measure of the amount of that energy present in a body, was clarified during the 18th and 19th centuries. Because all of the many forms of energy, including heat, can be converted into work, amounts of energy are expressed in units of work, such as joules, foot-pounds, kilowatt-hours, or calories. Exact relationships exist between the amounts of heat added to or removed from a body and the magnitude of the effects on the state of the body. The two units of heat most commonly used are the calorie and the British thermal unit, BTU. The calorie, or gram calorie, is the amount of energy required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. The BTU is the amount of energy required to raise the temperature of 1 pound of water from 63 to 64 degrees Fahrenheit. 1 BTU is approximately 252 calories. Both definitions specify that the temperature changes are to be measured at a constant pressure of 1 atmosphere, because the amounts of energy involved depend in part on pressure. The calorie used in measuring the energy content of foods is the large calorie, or kilogram calorie, equal to 1000 gram calories. In general, the amount of energy required to raise a unit mass of a substance through a specified temperature interval is called the heat capacity, or the specific heat, of that substance. The quantity of energy necessary to raise the temperature of a body 1 degree varies depending upon the restraints imposed. If heat is added to a gas confined at constant volume, the amount of heat needed to cause a 1 degree temperature rise is less than if the heat is added to the same gas free to expand, as in a cylinder fitted with a movable piston, and so do work. In the first case, all the energy goes into raising the temperature of the gas, but in the second case, the energy not only contributes to the temperature increase of the gas but also provides the energy necessary for the work done by the gas on the piston. Consequently, the specific heat of a substance depends on these conditions. The most commonly determined specific heats are the specific heat at constant volume and the specific heat at constant pressure. The heat capacities of many solid elements were shown to be closely related to their atomic weights by the French scientists Pierre-Louis Dulong and Alexis Therese Petit in 1819. The so-called law of Dulong and Petit was useful in determining the atomic weights of certain metallic elements, but there are many exceptions to it. The deviations were later found to be explainable on the basis of quantum mechanics. It is incorrect to speak of the heat in a body, because heat is restricted to energy being transferred. Energy stored in a body is not heat, nor is it work, as work is also energy in transit. It is customary, however, to speak of sensible and latent heat. The latent heat, also called the heat of vaporization, is the amount of energy necessary to change a liquid to a vapor at constant temperature and pressure. The energy required to melt a solid to a liquid is called the heat of fusion, and the heat of sublimation is the energy necessary to change a solid directly to a vapor, these changes also taking place under conditions of constant temperature and pressure. Air is a mixture of gases and water vapor, and it is possible for the water present in the air to change phase, i.e., it may become liquid, rain, or solid, snow. To distinguish between the energy associated with the phase change, the latent heat, and the energy required for a temperature change, the concept of sensible heat was introduced. In a mixture of water vapor and air, the sensible heat is the energy necessary to produce a particular temperature change, excluding any energy required for a phase change. Because heat is energy in transition, some discussion of the mechanisms involved is pertinent. There are three modes of heat transfer, which can be described as 1. The transfer of heat by conduction in solids or fluids at rest, 2. The transfer of heat by convection in liquids or gases in a state of motion, combining conduction with fluid flow, and 3. The transfer of heat by radiation, which takes place with no material carrier. The flow of heat in metal bars was studied analytically by the French mathematician Jean-Baptiste Joseph Fourier and measured by the French physicist Jean-Baptiste Biot in 1816. The conductivity of water was first determined in 1839, the conductivity of gases was not measured until after 1860. Biot formulated the laws of conduction in 1804, and Fourier published a mathematical description of this phenomenon in 1822. In 1803 it was found that infrared rays are reflected and refracted as visible light is, and, thenceforth, the study of thermal radiation became part of the study of radiation in general. In 1859 a physicist in Germany, Gustav Robert Kirchhoff, presented his law of radiation, relating emissive power to absorptivity. An Austrian, Joseph Stephan, established the relationship, now called the Stefan-Boltzmann law, between the energy radiated by a black body and the fourth power of its temperature. Ludwig Boltzmann established the mathematical basis for this law of radiation in 1884. It was in the study of radiation that Max Planck arrived at the concept of the quantum. Understanding of heat transfer by convection was developed during the period 1880 to 1920, although an equation describing such processes had been suggested by Sir Isaac Newton in 1701. Thank you for watching this video.